Okay, so first we're gonna start speaking about the control plane part. Then we're gonna go to the management plane security, and then the data plane security. But before we go there, we have to understand the networking device planes of operation. What plane is responsible for which traffic flowing or being, let's say, processed by a network device. And this applies to any kind of, doesn't matter the network device type, if it's a router, a switch, a firewall. So any network device, layer 2, layer 3, layer 4, layer 7, application inspection, they're going to have pretty much the same planes of operation in the end. So we have 3 planes. It seems that, let me reopen the presentation because it was a bug in there. There we go. So we have 3 planes of operation. One is going to be the control plane, and again, the name tells you exactly what it's going to be responsible for. The management plane, which is actually a subset of the control plane, and the data plane. And as you're going to see, the names tell you exactly for which traffic those planes are responsible back and forth. And because each of those planes are responsible for different type of traffic, it means it's going to have a different set of vulnerabilities which is open to, which means different security controls have to be implemented to secure each of those 3 planes. The control plane is responsible for traffic destined to the network device or sourced from the network device. It is used to learn information required for packet forwarding for the data plane. So the control plane is required so that a router learns enough information so it can actually perform packet forwarding back and forth. Doesn't matter if that device is going to do switching or routing of packets, or it's going to be a stateful firewall. It still is the control plane to be built to learn enough information about how to forward the packets and where to forward the packets. And this traffic is always process switched because it is destined to the router. Let's say if it's a router, is destined to the network device or sourced from the network device, which means it has to be punted to the CPU of that device, which means it's going to be process switched, which means CPU switched. Now, control plane traffic can be IP or non-IP. So traffic that falls down under this category is going to be routing protocols, which tell the router, for which the router uses to learn about destinations it can route out to, so for forwarding plane capabilities. IGMP and PIM, which are used for multicast routing, for example. NHRP, which is used in DMVPN, so it's scoped to build the DMVPN cloud. LDP, which is used in MPLS, and ICMPv6, which is used. ICMPv6 is part of the neighbor discovery suite of protocols in IPv6. Like for example, ARP for IPv6 makes use of some ICMPv6 packet types. So as you can see, though, all of those protocols are protocols which allow the router that in the end, based on those protocols functionality, the router can in the end do packet forwarding, user packet forwarding. So the routing protocols, IGMP and PIM for multicast routing, NHRP for running over DMVPN, LDP for MPLS switching, ICMPv6 for IP to MAC resolution, for IPv6 to MAC resolution, and for other purposes. And also we have some non-IP traffic, which is part of the control plane, like ARP, responsible for IPv4 to MAC bindings, which is required for the forwarding plane as well, and STP and VTP, which are protocols used by layer 2 devices in order to forward packets in a loop-free manner of STP, in order to populate the VLAN database from a central server via VTP. Now, the management plane is a subset of the control plane because it's still about traffic destined to the network device or sourced from the network device, but is used for a different scope. If in the control plane part, those protocols were aimed to help the router be able to actually forward packets in the end in the forwarding plane, then the management plane is still traffic destined to the router or initiated from the router, but has nothing to do with the data plane packets, with the user's traffic. It has to do with managing the device. So it's going to be traffic destined or initiated by the router, but with the scope of managing the device or for telemetry scopes, like network traffic visibility. And likewise, because it's traffic destined or sourced by the router, it's going to always be process switched or CPU switched. So it's not going to be Ceph switched ever. And this traffic is only IP, because nowadays we run pretty much only IP in our networks. Of course, we can run also non-IP traffic, but in general, if you want to manage a network device, you're going to do that via IP. So AAA via attack access radius, Telnet, SSH, and HTTPS are going to be for device management, and NTP, SNMP, Syslog, and NetFlow are going to be for network visibility or telemetry functions of the let's say network devices in general. And of course, we're going to speak about all of those, why do you use it, and how do they work, and how do we protect those protocols. Now, the data plane traffic is the actual traffic transiting the router or the device, not destined to the router or to the device. It is basically used, the data plane is used for active packet forwarding between devices interfaces, which is nothing else but users' traffic. And data plane cannot work without control plane being functional, because how can the router route a packet from interface A to interface B if it haven't learned about that destination to a routing protocol, or if ARP didn't work? So the control plane has to be built before data plane can work. But management plane doesn't need to be functional for data plane to work. So for a router to be able to route packets back and forth, it doesn't mean it has to be managed via SNMP or for Telnet on the router to work. And traffic, data plane traffic is in general Ceph switched, which means Ceph is going to be being done in hardware or in software, because we want line rate, low latency packet forwarding, which is going to be done via Ceph. I said in general because depending on the packet type, the router, even if it's a transit packet, the router may end up CPU processing or process switching the packet. Like for example, if a router has to fragment a packet, it cannot Ceph switch it because it has to punt it to the CPU, because the CPU has to do the fragmentation. The ASICs, the Ceph part, the ASICs can only do line rate switching or routing back and forward, but the ASICs cannot actually take actions to modify the packet like fragmentation. So it means that if a router has a transit packet which has to be fragmented, it has to punt it to the CPU. If a router has a transit packet which has to be, for example, which has to be, let's find another example. So if a transit packet has to be matches an ACL, for example, and the ACL has the login keyword, likewise the packet has to be punted to the CPU, because the CPU is the router's component, which actually is going to fire up the syslog message, not the ASICs, not the Ceph switching part. That's what I said, that data plane in general ideal is going to be Ceph switched. And traffic data plane wise is in general IP. Non-IP traffic can still be forwarded to specific encapsulations. Like for example, this is one question for you. Give me an example of a technology which allows you to forward, to encapsulate non-IP traffic and forward that non-IP traffic over an IP network. So which technology allows you to forward non-IP traffic over an IP network by encapsulating it into a specific protocol? Correct, Neil? GRE, right? So generic routing encapsulation. As the name states, that protocol allows you to encapsulate whatever, correct? MPLS, yes, pure MPLS, but it depends. Layer 2 VPNs, but it's a, yes, MPLS also allows you to do that, correct? in a different way. That's a good answer as well. But GRV is one, let's say, right, commonly known one. There are other encapsulations, other protocols as well, which allow you to forward non-IP traffic over an IP network other than GRV and MPLS.